Well, g'day flatties and globe defenders, it's Critical Think from Down Under. Now there's another flattie that has done a hit piece on one of my videos. The plain truth apparently thinks that ships don't go over the curve. Now he's actually hijacked the curve and invented this thing called the ether band. And it's very etheric, of course. And this also very versatile. This ether band can make ships disappear bottom up, and it can also prevent the horizon from rising to eye level. It can probably also bake a loaf of bread for you. Anyway, let's debunk the debunk and we'll see how far we get until we can give up in disgust. The Plain Truth has visited my channel, which is pretty good. I mean, we don't get many flatties looking at what the globe has to offer, but he is mistaken about some things and has a few misconceptions. Let's look at something here. This is something that was on my video about crepuscular rays, and he made a comment, and I asked a question about why is the sun below the horizon in that picture, and the answer I get is that the sun is never below the horizon in either model. So you can tell there how much understanding of geometry and very basic globe earth facts that this person is familiar with. It makes you wonder whether they have a really good argument for anything else, doesn't it? And here's another thing. That's so let's just say then the sun is above the earth then. In that picture, what would be the distance of the sun if it was 3,000 miles high? Can't calculate it. The sun is simply away in the distance. What causes boats to disappear bottom up as they move away? What is blocking the object? And refraction is the answer. Refraction each and every time. And why is the horizon not rising to eye level? Refraction. And because I said I wanted to keep my refraction constant by changing height, he says, well, where is my data to support refraction being constant? I mean, I said 30 minutes, but it only took me 10 minutes to take my observations. But in 30 minutes, I say, the refraction is not going to change enough to obscure the whole bottom of the boat. So we eliminate that variable and say, over the period of about 30 minutes, refraction is constant so that we can eliminate it as a variable, not ignore it. But where's my data to support this assertion that refraction might be constant? Okay, I didn't have that. I wasn't anticipating this question. And I also like to say that since when is saying refraction mean anything? And of course he wants to focus on the fact that I don't have a time lapse of 30 minutes to show that refraction doesn't change. Now, by refraction I mean the effect over the horizon that causes the horizon to rise up or rise down, or causes things to be more visible or less visible over the horizon. The refraction can have this effect, but over the period of 30 minutes or so, it's unlikely, extremely unlikely, unless you get gross weather changes, that this would have any effect on my change of height observation. So I'm keeping refraction constant and just changing my height. But anyway, since you asked for it, here it is. Now on this particular day, there wasn't much refraction, and you're going to have a lot of trouble there trying to pick out the inferior mirage. You're going to have to get your microscope out there. But you can tell that the water level does not rise to cover half the ship, neither does it go down to reveal the hull of the ship. So it's fairly safe to say that refraction doesn't cause the water level to rise or lower any in that particular time frame, which in this case is 25 minutes.
Okay, what you see depends on refraction, which is exactly what I've been doing in my past handfuls of videos. I've been hammering that home. Now, my challenge to Critical Think is you have to go out, precisely because of what you just said, you have to go out again and again and again.
Well, no. did you listen to what I said? I said, yes, it does change from day to day. And the aim of my observation here was to eliminate refraction as a variable, to show that changing height can change the amount that is visible over the horizon, and the refraction is a constant. So therefore, the refraction is not the cause, the change in height is the cause. Yes, you can go out on a different day and see a different thing, and I have done that, and you'll get to see some of that here. And the other thing is, you see, you talk about me doing strawman, there's the strawman right there. Oh, go out on a different day and the refraction will be different. Yeah, but that's not what I'm doing here. And the other thing about refraction always being the answer, unless you can establish a causal relationship between refraction and the amount of ship visible, then you can't just say refraction. Yes, there is a certain amount of relationship that will change the amount of a ship hidden over the horizon. That's definite. But I'm eliminating that as a variable by doing a height observation within a few minutes of each other. So it doesn't matter if the refraction is different on a different day. The result will be the same. I can change my height on a different day and I'll get the same result. So I'm not depending on a particular level of refraction that I cannot measure. I'm able to measure my height to within about a metre. And the other thing is, one thing I wanted to mention, you can't just say, oh, that's due to refraction without some corroborating evidence. Like I might as well just say, oh, the ship is disappearing bottom up because of chocolate cake. What evidence do I have? Or we could just say, oh, because of coffee. I mean, everybody on the ship, they probably drink coffee. I mean, if you did a survey of the people, the crews on these ships, they'd probably drink coffee. So the crew on every ship drinks coffee. The ship disappears over the curve. So therefore, the reason the ship disappears over the curve is because the crew drinks coffee. Now, if you think that's silly, well, that makes just about as much sense as your argument that refraction occurs, therefore refraction is the cause of the ship disappearing bottom up. The two are not necessarily related. You have to establish a causal relationship.
Because when he shows us this cargo ship with the containers on it, if he went out 3 hours earlier or 3 hours later or whatever, because he's going to talk about the independent variable, which is his height. So he's wiggling his height. He's up high 15 meters right here, I would think. He's 15 meters high here. Then he goes down to the shoreline. Now, again, the point is that 2 days earlier or 2 days later, if he does the same observation and that ship is still there, he's going to see that ship differently.
Yes, of course I'm going to see that ship differently. But again, the point is that's not the point of this observation. If on that different day I would change my height, again, I would still get more of the ship disappear as I lower my height. This is a globe thing. Can only happen when there's curve. It cannot happen on a flat Earth.
Yeah, and then is he going to cherry pick which one he wants to support his position?
Right, which in his...
I think we can all accuse each other of doing that, can't we?
Yes, we can all accuse each other of doing cherry picking, and flat earthers are really notorious for it. Now, I don't need to cherry pick. I can go out on any day. The problem is, if I go out on a day where there is significant refraction, all that's going to happen is some flat earther is going to say, oh, look, you've got an inferior mirage there. That's why the bottom of the ship is gone. It's the inferior mirage. And so it gives flat earthers an excuse. So I like to take observations on days where there's no or very, very little inferior mirage. And that eliminates that excuse. However, on this day, there was a little bit of inferior mirage. I mean, not much. I've seen it much worse than that. But you're already using it as an excuse. On that tiny little bit of inferior mirage, it doesn't explain the huge difference. You've never explained why it can suddenly make half a ship disappear when we go down, 12, 13 metres. Oh dear. So this is what you do. You go out different days and take different observations. You start making conclusions. You say, oh look, on this day I have an inferior mirage and I can't see this. And on this day there's no inferior mirage and I can. Therefore, the inferior mirage is the cause of me not seeing it. So I have gone out on a different day. This is just one of my observations. I've got many of them. But a clear day now. Can see clear over to Tangalooma Resort, which is 28 kilometres away. And from my same spot. And let's have a look at what the difference in height does. So yes, we can see the houses and buildings near the shore, but there's plenty of beach below that you can't see over the curve. So let's go down now, reduce our height, and what do we see? You see that? That can only happen on a globe. On a flat earth, you would still be able to see clear to the island, down to the beach. Now, also, this is a very particularly good day. I mean, you're going to have a lot of trouble finding any inferior mirage there. You're going to have to get your microscope out, flatties. Try and work out, there must be an inferior mirage there somewhere. There's houses missing. There's got to be an inferior mirage. That's the only explanation. It couldn't be that the Earth is curved, even though that's a pretty damn logical explanation. Fits all the observations. Talk about this. How does that ship get to be so much disappeared? And a flattie will say, look, there's about 2 millimetres of inferior mirage there. Of course, 2 millimetres can hide 5, 6 metres of ship, no problem, if you don't do the maths.
Yeah, and it's not, but anyway. Okay, he just created a straw man because no one is saying that about his footage right now. He's creating a scenario that he can absolutely just tear down. He said flat earthers will say that these objects are getting blocked by high waves. Well, there are no high waves here. Well, then you just wasted 2 minutes of our time.
Yeah.
Because no one's made that accusation here.
Okay, so let's just get this straight here. I'm supposed to know that the plain truth is going to come to my video and not make a comment about the waves. Now, how am I going to know that when I'm making the video? That is one of the most silliest things I have ever heard, that I just wasted your time. I mean, you're not the only flattie out there, and there are plenty which will talk about the waves.
From this example, that even a small wave on the surface in front of us will block off a much taller and larger ship in the distance.
Well, any kind of swell or any kind of wave height, that is going to cause blockage. It really is out to sea. Even if the waves on the shoreline are relatively shallow and not doing much, out to sea, they certainly are. So out to sea, what you're getting probably 2.5 meter high swells.
So you see, people do make that argument.
Okay, so he gives the measurements and his pixels, and he's got a P1000. The height of the ship is about 78 feet or 24 meters. Okay?
The fact is, I'm about 15 meters in height.
Okay, so now he's giving you where his location is. He says he's 15 meters in height.
But the horizon is not there 15 meters high on the ship. The ship is on the horizon. This can only mean one thing, flatties. The ocean curves away. You don't see it go off into the distance. And if you're thinking,
Okay.
just make note that he just stopped that there. What comes next in my video is very important, and what comes next in this video is important too. So listen carefully of what happens.
Okay. So now his argument is that he's up 15 meters. He thinks that this horizon should be higher up. Not blocking the boat, but that the boat and the horizon should be lifted up. Can you?
No, not the boat lifted up, just the horizon. The boat stays where it is. It's on the water. It's not just going to float up into the air. The boat stays there. The horizon should be lifted up. You got that?
See anything wrong with this image right now, Mark? How would you analyze what he said? That the... Let me go back right there, okay? He says that the water line, because he's 15 meters high, the water line should be there. Can you see anything wrong with this image? How would
Now, wait for it.
you analyze it?
On a foggy day, the horizon is at your feet. So depending on how much moisture or muck is in the air, depends on where the horizon would appear.
Okay.
Let's just move right along for now.
Okay. Now, from the horizon up is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. I think it's more than 17. So this is not even centered. He's got more sky than he has water. And you know what would happen if he eliminated a little bit of this sky? This horizon would be right where the he says it should be.
But you're just saying the way the camera is pointing.
Yeah. And I'm not saying that he deliberately did this, but he's not looking at it correctly. He's got more sky. This is not centered.
Yeah.
Okay, so deal with that, Critical Think. I think we're going to stop right here because.
Oh my God, really? You just didn't say that, did you? That the horizon is where it is because the camera's not centered? Seriously, you said, oh, okay, you asked me to deal with it. Here, let's deal with that. There you go. It's centered now. But look at that. The horizon still doesn't rise to where it should be. The horizon should be 15 metres on a flat Earth. It should be 15 metres off the ground or sea level, not ground. Now, this ship is floating on the ocean, right? I mean, we can agree on that, right? Or you're going to deny that too. And this water on a flat Earth is flat and level, right? Right. So 15 metres above the surface of that ocean on a flat Earth is going to be where that red line is. So we should see the horizon rise in the distance to that red line, regardless of where you're pointing your camera. Now, that red line is eye level on a flat Earth, but it's not eye level on a globe Earth because that ship has already sunk down a bit due to the drop because of curvature. But we're talking flat Earth right now. We're assuming flat, and we're finding that flat is very much not supportable here. I've put together an animation a while back to show, first of all, there's a completely flat surface going off into the distance, into infinity, and the eye level is at the top of that ship, and you can see the horizon rises to eye level. And now we'll tilt the camera.
Yeah. Now let's move the camera up, move the camera down. It doesn't matter which direction you're looking, the horizon still stays in line with the ship. So camera tilt, eye tilt has nothing to do with it.
And this is duplicated in real life. You can try it yourself. So here's the crux of the thing. You see that buoy in the foreground? You can see water behind it. Well, until the water reaches eye level, you should be seeing it behind the ship, just like that. I mean, the only reason the ship appears to be on the horizon is because there is a horizon, because the water is curving away. If the water was flat, you would see it beyond the ship. Here's some pictures I took a while ago, and one's doctored, of course. The bottom picture is the picture of the ship, not quite on the horizon. It's actually in front of the horizon. You can see some water behind the ship. But if the Earth were flat, you'd see much more water behind the ship, similar to what I've doctored up there in the top half of that picture. This is how it would look on a flat Earth. It doesn't look like that. And of course, people get to the argument of, oh, you can't see that far. That's why you don't see that. Well, we'll deal with that. First of all, now we'll talk about this. This is why you should see the water beyond the ship. If the Earth is flat, see this guy here up here, he's high, he's almost level with the bridge of that ship. He can see the water past the ship. If the water goes off into the distance, his eye level be at the top of the ship, he would see the water up to that eye level. There, you can see he has line of sight to the water behind the ship. Don't trust me on this. Do put model on the ground, get a piece of string. If you're looking over the top of something, you can see the ground behind it. Do it on the floor of your house. Do it on a concrete path. You can see this is just plain obvious. It's just a feature of flat surfaces. Now I got criticised for not putting the ether layer in there. Well, here, look, let's put in some atmosphere and at about the top. About the bottom metre or so, let's just put in an ether band there. There's some turbulent or in temperature inversion or something which might cause an inferior mirage. Moisture in the water can do that. Temperature inversion can do that. And let's see, this guy here is 2 metres tall. He can already see over the top of it. How's it going to stop him seeing the ship? You're going to have to work that one out. You're going to have to work out how that can happen because everything's flat. Your ether band is there just above the water. We've seen that because the guy up high, even though you say, oh, there's an infrared mirage there, it's only on the bottom of the ship. So I've given you a generous meter there. And how are you going to work that out? And here's now, when you have a curved surface, it doesn't have to be water. It could be just ground or a road and something behind the curve. It doesn't have to be a ship. But this is how changing in height can change both the position of the horizon and the amount that you can see. I mean, that's pretty simple. Everything works for a curve. It works exactly as expected. You take refraction into account. Refraction can change this a little bit, but refraction cannot cause the whole half of ship to disappear. You're going to have to establish that relationship because it works just fine on a curve.
The horizon
if you're
is the result.
Thinking, as some do.
Okay, so he says right now, again, he's creating a straw man. If you're thinking, okay, nobody's making this claim about what you're about to destroy right now. No one's making this claim.
That's just the limit of sight. You can't see beyond that. That's why you can't see the water. Well, I've got a picture here.
Okay, yeah, if you wanted me to go...
Did you hear what he said? He said, I'm creating a straw man, and nobody says that you can't see beyond that horizon. Well, his mate just said it. He just said it a just short while ago. I'll replay it again.
On a foggy day, the horizon is at your feet.
So he goes on to say that you can't see that far. That's what he just said. I'm not creating any straw man. That's what his own guest just said. And he complained about not having information about those pictures. And yeah, all right, acknowledged. He didn't have all the information about those pictures. But here it is. 4:53 p.m. I take this picture. You cannot see the water behind the ship. And it's not because you can't see that far. And then at 5:02 p.m. we see I go down in height and you can't see the bottom of the ship. And there is an inferior mirage, yes, but it's not big enough to hide a bottom of a ship. If you want to make that assertion, you need to work out how that can happen. because it's just not possible. You're going to have to prove that. And the horizon here is in front of this ship. You go down, the horizon comes closer, just like in that diagram. So the guy in green has a horizon that's closer than the guy in orange. So that ship is not on the horizon, no. The horizon shifts according to refraction, according to how high you are. Yes, just remember, I said the horizon shifts because of refraction, but also remember that the refraction does not change significantly in a few minutes. It cannot change that much to hide half a ship. And then a few minutes later at 5:07, I go back up the hill and the ship's moved on along a bit, and I've taken this picture. In the original video, this picture was accidentally stretched because that's what my editor does automatically. If I forget to correct for the stretching, it's going to look stretched. But this is the right proportion here. And so you can see beyond the ship, but you don't see water beyond the ship. This is because the water is curving away. And you can say refraction all you like, but I can say drinking coffee. It means exactly the same thing. I can say chocolate cake. Unless you can establish a causal relationship and describe how it works, you've got nothing.
Okay, look. Look at these angles, he says. Where's your measurement of this? All you did was type this in. You can't show this. How did you figure that out, Critical Think? How did you figure that out? That .005. Where'd that value come from?
Really? I mean, really? All the numbers are there on the diagram. It's just a simple trig calculation. There's a triangle, 1 metre on one side, 11,660 metres on the other, and you take the inverse tan 1 over 11,660. And that's how you get the angle. Now, if you're unable to do these simple trigonometric calculations, then there's a website which can help you with this. And we plug the numbers in there if you don't feel confident in doing the calculation yourself. And you can see that the angle is 0.00491, which I have rounded up to 0.005. So there you have it. There's plenty of other silly stuff in that video, but I just don't have time to deal with it all. And watch out for a live stream perhaps coming up soon, where I'll be able to discuss some of these things with the plain truth.